Okay, so welcome back. And we have the last talk of this morning session by Prasad Perlekar. So please, Prasad.
Yeah, thanks, Alessandra. And let me start by thanking the organizers for this wonderful meeting. So what I'm going to be talking about today is on turbulence modulation by Bubbly flows. And this work was done in collaboration with Vikash, who was a graduate student here, and now he's in Auditor, and with Dhruva, who I think most of you know. So the motivation was very simple. It was, based on also something which I was doing earlier, is the question that bubbles are present everywhere. And many of us earlier have even listened to the talks about particles and bubbles in flows, but at least in the community for a long time, the stress was on bubbles or particles whose size is sub-Kolmogorov scale. On the other hand, in variety of natural phenomena, what happens is that the bubbles that are present, something like, when you're boiling water for tea, or in a bubble column reactor, or in hydrothermal vents, or in hydrothermal vents, what you find is that you have large bubbles, and these bubbles also generate flows, also modify the transport of heat or reactant or gases which they hold. So the question would be that what are the flows generated by these bubbles? How can we understand them? What is the statistics of these bubbles? Maybe the center of mass velocity PDF, the Lagrangian statistics. So those are the broad questions that we started to think about. And one of the nice experimental setup that we came across, which we then thought would be one thing which we should try to understand, was this 20 bottle tunnel experiments, where what they have are bubbles which are rising due to buoyancy. And on top of it, they can also apply large-scale stirring on it, so that you would have a system in principle where bubbles are rising. They have their own wakes. There is also large-scale turbulence which interacts with these bubbles, and the wakes of the bubbles also modify the dynamics of the bubbles which are following them, right? So this is more or less the setup, but we should also be careful about what are the different length scales in the problem. So the typical injection scale is 50 to 70 millimeters. The diameter of this bubble is roughly 10 to 12 times the Kolmogorov scale. So these are really large bubbles. And when there is an external stirring present, the Reynolds number is of the range of, it's moderate, 160 to 265. And if you want to characterize such a system, the non-dimensional numbers are quite a few. Now, no more will just work with the Reynolds number, but you would have Reynolds number, the Galilei number, which is the ratio of buoyancy to viscous forces, the Bond number, which is the ratio of buoyancy to surface tension forces. You have to worry about what is the density difference, whether you're looking at water bubble in air, air bubble in water or air bubble in mineral oils. And if you have external stirring present, then you have to ask whether external stirring is comparable to the rise velocity. So the typical velocity fluctuation introduced by external stirring, is that comparable with the rise velocity of the bubble or not? So that's given by this Bubblin's parameter. So we have a very broad parameter range where we can work. And the question is then, the flow that they observe in the experiments, does one need to choose exactly the same parameters as experiments? Or as we know in turbulence, right, whether you do Reynolds number 100, 1000, broadly speaking, you would get many features of Reynolds going to infinity. So the question is then whether we can work in a broad range of non-dimensional numbers and tell something about statistical properties of these flows. So what was observed, of course, when so many experiments have been done, one thing that most experiments measured was the energy spectrum. And the earliest of these studies were done by Lance and Batal in 91, where in presence of external stirring, they found something remarkable. And that was that in presence of bubbles, you have up to the size of the bubbles or frequency scales of the bubbles, you have a 5/3 scaling similar to the standard Kolmogorov turbulence. But for scales which are smaller or frequencies higher than the bubble frequency, or for scales smaller than the bubble diameter, you have a -3 scaling. And then the question was, how do we understand it? Because there is not the standard dissipation range anymore, but something which is regular but has a slope of -3. Now the answer to this question was given by saying that what's happening is, as the bubbles are rising, they generate eddies, and these eddies are immediately dissipated in the vicinity of the bubbles. So bubbles don't lead to any transfer of energy to smaller scales. It's immediately formation of some structures, and those structures getting dissipated off. Now, then they argued that if you do a simple dimensional analysis, you would suggest that energy production then is equivalent to energy dissipated in the wakes times K inverse, and that you balance by viscous dissipation, and that gives you K raised to -3. This picture suggests that none of the nonlinear transfer mechanisms, the surface tension of the bubble, nothing of those things are important. All that matters is what is the energy injected by buoyancy, and you have to balance it with viscous dissipation. And now these experiments were done for air water system. So the output number is fairly large, 0.99. And then the obvious question is that is this true for all gases? For example, if you have methane bubbles rising in the ocean and the flow that they generate, would it be identical to this or would it be different, right? And that's again remains an open question at some level. So then we said that, okay, let's ask this question, let's start to understand it, and of course do a literature survey. So we started off with a very simple setting. Let's have large bubbles which are rising because of buoyancy. There's no external stirring present in the system. Whatever flow is generated by bubbles. And then we said, let's write down what are the non-dimensional parameters, and we wrote down all of them, which, as I mentioned earlier, are the Galilei number, the bond number, the Atwood number, the viscosity contrast, the volume fraction at which the system is working. Now, most of the experiments are done at small volume fraction, around 2.5%. So we said, let's keep the volume fraction fixed. Let's not worry about that. But still have to worry about the viscosity of air and water, which has a contrast of around 100. You have very large density difference between air and water. So output is 0.999. The bond number is around 1, and the Galilei number varies between 200 to 1000. And so let's ask then that if you have this wide range of parameter scales, let's see whether we can make sense of what are the flow properties numerically. And this was challenging because we know already from looking at literature about single bubble dynamics that we cannot attain these parameters in a numerical simulation. It becomes numerically prohibitive. So then, of course, the straightaway thing is, can we do cheating? Can we work with the lower output number and still get the same thing as experiment? Can we, instead of working with a viscosity contrast of 0.02, can we work with 0.2 or even 1? So those are all the questions that we would came across. So let's start. And as is typically done, this problem was first attacked by the people who are doing experiments themselves. And in a nice work by Irene Mazzele and Detlef, what they said was that let's think of these bubbles as point particles. So these are small particles which are rising due to buoyancy. And let's do a full 3D DNS. And let's ask the question, what kind of flows are generated? Are these stationary flows? And what is the spectrum? And what they found quite remarkably, that the flow that they observe first are non-stationary. At long times, so the time is increasing like this. So at very early times, you see something like a 5/3 appearing. And that's quite non-trivial because that would mean that in 2D, with these point particles, you have a 5/3 scaling, something like an inverse cascade in 3D, sorry. But at later times, everything starts to die down. You have more or less at large scale some energy being pumped in, and in all other modes, there is very little energy. This is when you have lift forces present on these point particles. If you switch off these lift forces, something else happens. You still start with something which looks like 5/3, but then this region remains persistent for long times. So even at the level of point particles, it's not at all clear what would happen when you have gravity and when these particles can modify the flow via two-way coupling. The answer seems to depend dramatically on whether you take into account lift forces, whether you don't take into account lift forces. Is there an inverse cascade even at short times? I don't know. However, it's very clear that all these results are far away from experiments. They have nothing to do with experiments where the diameter of bubble is at least 100 times larger than what they had chosen. So maybe all these effects that they are wondering about might be valid when you have Stokesian bubbles rising. One needs to look at it. But for large enough bubbles, it looks like these point particle simulations won't be of any use. So then let's go ahead. Let's ask what happens when one does fully coupled simulation. So while Detlef and others did it before them, already there were people, mostly Greta Tryggvason's group, who were doing similar simulations of a swarm of bubbles rising due to buoyancy. And what they found out was that if they just plotted the energy spectrum, then the energy spectrum has a slope of minus 3.6, which looks okay, close to something like -3. Again, two things you have to keep in mind, that the Reynolds or the Galilei number that these simulations were working at was around 20, whereas the experiments typically have Galilei numbers which varies between 300 to 800, something like that. Now, but straight away, one thing is clear, that even at this low Reynolds number, these experiments are showing, sorry, these simulations are showing that the wakes of the bubbles interact with each other to give you a non-trivial scaling in the energy spectrum. And then they concluded, just by looking at the spectrum, that look, the argument of Lance and Batal therefore is valid. What you have is that buoyancy balances surface, not surface tension, sorry, viscous dissipation, to give you a -3 scaling. The bubble wakes are important and surface tension plays no role. To us, that was quite counterintuitive, because typically you would expect that the buoyancy force would act at scales which are comparable to bubble diameter, whereas viscous dissipation would act at much smaller scales. So how are these two things, which are acting at very different scales, somehow are balancing each other in a scale by scale manner? So that was the question that we asked ourselves. Now, before we go ahead, it's important, once, using these simulations, that we have realized that the bubble wakes are important. Let's see what kind of beast we are looking at when we want to do simulation of such a system. So let's look at the dynamics of an isolated bubble first. So here are 3 pictures taken from the Gallery of Fluid Motion by Van Dyck. And what you find is that if you have a Stokesian bubble, then you have the standard Hadamard-like solution. These are streamlines. If you increase the Reynolds number, so this is air bubble in mineral oil, you have a laminar flow, but you already see circulation and you have a spherical cap bubble. If you further increase the Reynolds number, then actually the wake of the bubble becomes turbulent, right? And people have actually spent quite some time on it. There is this very nice paper by Bhaga and Weber where they have a phase diagram based on the Reynolds and bond number, which characterizes the shape of the bubble in different parameter regime. Well, most of the experiments are done in a regime where Reynolds number is roughly around, in this regime where the bubble is either ellipsoidal mostly. Okay, so that's one thing that we would like to see if our bubbles are ellipsoidal or hit a regime where it's like this. And clearly, as we go on increasing the Reynolds or Galilei number, we will have different types of flows or different types of wakes. So the question again is that we need to then see how does the collective behavior of this entire system looks like. So how do we go about it? Well, we do a numerical simulation. Sorry for this thing here. I don't know how it came, but what we do is solve Navier-Stokes equation coupled with a surface tension force. And the surface tension force is modeled in the same way as Chandrasekhar would do, that you think of the bubble as a bunch of points, and at each point you apply a Dirac delta force. You find what is the local curvature. Whether you are in the bubble phase or in the liquid phase is determined by a color function, which is 0 in the bubble phase, 1 in the liquid phase. The bubbles are modeled via a front tracking method, where each bubble constitutes of points which are connected to each other via Voronoi-like tessellation. And in a single bubble, you have roughly 10⁵ points. And as the bubble deforms, the points have to constantly disappear and reappear again. So this is a slightly non-trivial algorithm where you have a Lagrangian front of points, which is connected with each other with a nearest neighbor interaction. And then these points are moving together and giving you exactly what would happen for a bubble. So this is like, indirectly doing a molecular dynamics simulation where you have to take care of the nearest neighbor distance and linkages along with the Navier-Stokes simulation. So let's start by looking at the dynamics of single bubble for different parameter ranges. Remember, I told you that the Galilei number, the Atwood number, and the viscosity ratios, everything matters. So what we did was we said that let's first look at the dynamics of an isolated bubble, first at low Atwood number, and by increasing Galilei. Now, one thing becomes clear that when the Atwood number is small, the bubble more or less remains ellipsoidal, and the wake of the bubble is quite regular flow structure around it. When you increase the Galilei number, you have a much longer wake, and the bubble itself is doing oscillatory undulations. On the other hand, if you keep Galilei more or less fixed, but just crank up the Atwood number, then a single bubble trajectory becomes extremely complicated. You have a bubble which is doing zigzag motion, and it also rotates as it goes up. And the wake of the bubble looks like a horseshoe vortex pattern that is people who do channel flow, they see it quite regularly. So then the question was, well, single bubble depends so dramatically on Galilei and Atwood number. Can we ask now, how does the collection of bubbles do? Rahul, do you have a question? I see a raised hand.
Rahul, do you have a question?
Yes, I do. I was muted. Can your bubbles break?
No. So in this scenario, and also, because the bubbles are not deforming a lot, so they won't undergo breakup anyways. Okay, but within the algorithm, the bubbles don't break. But also we ensure that the Galilei numbers and even in the experiments, the deformation is such that you are far away from the breakup regime. Yeah.
Okay, thank you very much.
So now that we have seen that the dynamics is very dramatically changing and depends crucially on what are the Galilei and the Atwood numbers are, let's be brave, let's say, and look at how does a suspension of such bubbles behave. So now here is a movie for Galilei 420 and Atwood 0.04. Remember, a single bubble trajectory is a bubble which is oscillating, and the wake flow looks something like this. You look at the collection. So I'm showing now a subset of the simulation domain. You see a collection of bubbles, and well, when you look at them collectively, the wake structure is not clear. It's not like this. It looks something like the complex flow patterns which are generated. You do the same thing, although if you look at carefully at an individual bubble, you would see still this oscillating motion. Now let's look at what happens to the case when Atwood is large and Galilei is 360. Remember now the individual bubble trajectory is zigzag motion. Let's see what do they do. So here again, if you watch carefully, individual bubbles start to make zigzag motion, but then you start to see that the vortex flow structure is again extremely complex. Each bubble is interacting with bubble at its wake. So then we made a strong hypothesis that, is something like what is observed in variety of physics problems, that although the individual entity that constitute the suspension or that constitute, let's say, a metal, if you're thinking of the statistical property of metal, then although the individual entity is very different, the collective behavior maybe has the similar or identical statistical properties. So with that, we will go ahead with this hypothesis and we will see how good is this hypothesis by comparing our results with experiments. All right, so let's go ahead. So let's first, just for the sake of argument, check whether as we increase Galilei number, what happens to the bubble deformation within the experimental range? Are the bubble deforming a lot so that they are going to break up? The answer is no. For all the Atwood numbers that we have looked at and for a range of Galilei numbers, if you see the surface area of the bubble in comparison to a bubble which would have been spherically shaped, the bubbles are only slightly deformed. They are not deformed dramatically. And so they are more or less ellipsoidal shape. Of course, the surface area or the deformation increases as we increase the Galilei number, but we are far away from any breakup regime. Now, the next thing, of course, is that just to see whether our simulations are behaving correctly, we, of course, see that for all the runs. So here are the list of simulations that we did for a large range of Galilei number and bond number and the volume fraction. We kept more or less in the same range as experiments and varied output number for very small values, from very small values to values which are large, not as large as experiments. So experiments would have output of 0.99. We went all the way up to 0.9. Now, if you do the energy budget, what you realize is that in the steady state, if there is one, then the surface tension contribution and the kinetic energy, because you are in a statistically steady state, the time derivatives, of course, would be equal to 0. So what you should find is that all the energy is dissipated is balancing the energy injected by buoyancy, okay, in the total box. And that's what we find with a very good accuracy, that our simulations are correctly predicting that all the energy that is dissipated by viscosity, it's balanced by energy injection. So let's go ahead. Now that we have measured energy injection and energy dissipated, let's check the argument of Lance and Batal. So what Lance and Batal said was that, look, most of the energy injected by the bubbles is dissipated in the wakes of the bubbles. So now one can estimate the energy dissipated in the wake simply by realizing that it's equal to the drag velocity, so the drag coefficients times the velocity square divided by the diameter of the bubble. And from, you plug in the value of drag coefficient of a bubble depending upon what your Galilei number is. Typically it's order 1. So you plug it in, and what we find is that, so the pluses are one of the 3 quantities. I don't remember exactly which, but it's very clear that all the 3 estimates are very close to each other. And that implies that the energy dissipated in the wakes is indeed close to the energy dissipated because of viscosity. It's same as energy injected. So that means that the argument of Lance and Batal is not too wrong. Okay, excellent. So now let's then ask the next argument. How can you argue that the nonlinear terms are irrelevant within an experiment? The way they argued was that they said that, look, the time scale of energy transfer due to nonlinearity is going to be way larger than the time scale of energy production by buoyancy and the time scale of energy dissipation. Well, in our experiment, in our simulations, what we find is that although this ordering is valid, but as you go on increasing the Reynolds or the Galilei number, the time scale for energy production by buoyancy starts to become comparable with the time scale of nonlinear transfer. So that means that in the experimental regime, the argument of Lance and Batal is not completely clear, right? It's true if you are at low Reynolds number or low Galilei number, but in the range where experiments are done, where they observe a -3 like scaling, there this argument is not clear. So then the question is, okay, how do we go ahead and check things? So before we do that, let's ask how good are our simulations. So what we looked at was PDF of velocity fluctuations. And here is the first non-trivial and counterintuitive point according to me. The thing is that typically when we do homogeneous isotropic turbulence, what we observe is the single point PDF are Gaussian. On the other hand, in these bubbly flows, what you observe is that the single point PDFs have an exponential tails, right? So at least in the plane which is perpendicular to the gravity direction. What does that imply? That implies that the velocity, the single point velocity itself has long range correlations, right? This is very similar to what is observed in force correlations in granular material. Now, it's not clear to me why in these bubbly flows it's happening. It's something we are still trying to understand. Of course, you expect that the Z component of the velocity is positively skewed. That's expected because, because of buoyancy, your bubbles are rising up. There are more positive velocity fluctuations than the negative velocity fluctuations. So that's clear. But why you have in the plane which is perpendicular to the gravity or the XY plane, why you have exponential PDFs and not Gaussian PDFs, which is what both experiments and simulations observe, is not clear. We believe that the differences that we start to observe in the tails of our distributions has indeed to do with the non-trivial wake structures, which depends crucially on the Galilei numbers. But the core of the PDFs is very well represented by our simulations and the experiments. So let's now see how does the energy spectrum looks from our simulations, what we find is similar to experiment. As we hit large enough Galilei number, our energy spectrum starts to show -3 scaling. So that was good. But this simulations were at low Atwood number. So then you would ask that, well, is this low Atwood number physics? What happens at high Atwood number? So then we had done, of course, simulations at high Atwood number. And when you do, so we did it at Atwood 0.09, which is what I had showed you earlier. We then did simulations at Atwood 0.9. And fortunately for us, there was another group by Innocenti and others who did simulations at much higher Atwood numbers, 0.99, with simulations which also have a mesh refinement techniques inside. And what they find is that irrespective of, so they call what we call as Galilei, they call Archimedes, irrespective of the Atwood number that we had chosen, right? The energy spectrum shows exactly same scaling as what we had shown in our small Atwood number. So Atwood 0.09, large Galilei around 300, -3 scaling. Our earlier work at Atwood 0.9, Archimedes 358 is the red curve, sorry, is the green curve. Archimedes 185, but even further cranking up Atwood number, exactly the same data. And the experiments of Rebu, which, okay, I'm not too sure about how they were done for large and small scales, have a minor overlap at intermediate scales. But what we did was, we said, why to go this way? Let's do exactly what experiments do. So experiments put probe, measure velocity fluctuations. From there, estimate what is the energy spectrum. So we did the same thing in our simulations. We compared, so now here, the blue colored data is the simulations, are the experiments of Loze's group. The blue data is our simulations. The orange data is the experiments of Loze's group. And they fall on top of each other. Of course, the experiments are at even higher Atwood number. They are at 0.997. So one observes something really remarkable, that as far as the statistical properties of the liquid velocity fluctuations go, they show the same scaling behavior for a wide range of Atwood number. It's irrelevant what is the density contrast. It's irrelevant what is the viscosity contrast, which means what you're thinking of are objects which generate some wake flow. And this flow interacts with other bubbles or other objects which deform and do their stuff. And that creates a complicated flow pattern, which seems to be very universal. So then let's ask, so with all these things that we were now very sure that irrespective of low or high Atwood number, we are able to reproduce the physics, which is observed in both experiments and other simulations. Let's ask ourselves the question, is the argument of Lance and Batal correct? Is the energy transfer extremely local? You inject something, it gets immediately dissipated by viscosity. So to do that, we use the standard technique of fluid dynamics, that is to look at the scale-by-scale energy budget. And we followed what INC or Orszag had followed. And so this is a standard, I mean, to this audience, I need not even explain what the scale-by-scale budget equation is. But what you have is that the nonlinear flux plus the flux due to surface tension is balanced by viscous dissipation, the energy injected by buoyancy, and if there is external stirring, you have to add the additional term because of stirring. So let's first look at the case where you don't have external stirring present. That's this case where you would have the nonlinear transfer plus the surface tension contribution, or the transfer due to surface tension, should balance the energy dissipated by viscosity and plus the energy injected by buoyancy. So here is what we get for our largest Reynolds number. And that's interesting. Now remember so when you look at all these fluxes, remember in the scale-by-scale equation, these are cumulative fluxes, right? So if something saturates or becomes constant, that means that here, if you wanted to look at the transfer, you have to take the derivative of this. So this clearly shows what I was telling you earlier, that most of the energy injected by the bubbles is at the scales of bubble diameter, not at the scales where dissipation is taking place, which is denoted by the orange line. So that straight away tells you that this idea that whatever is the energy injected is immediately dissipated by the viscosity does not seem to be true. There needs to be another mechanism which transfers energy to small scales. So what is that mechanism? It turns out that you have both surface tension, which initially absorbs energy and then pumps it back to the small scale. So you can think of it, if you want to physically think about it, you can think that as the bubbles are rising and deforming, they are absorbing energy from the fluid. And then as they relax back and do capillary oscillations, they pump energy back into smaller scales, somewhat similar in a qualitative understanding as what we think about polymers. You have a non-zero, non-linear flux also present. However, quite remarkably, if you add these two fluxes, which would actually tell you what is the net production in the system, they actually give you a curve which indeed has a scaling which goes as K inverse. So if you take a derivative of the net flux or net transfers, which would give you the production to these scales, you see that it's proportional to the epsilon omega times K inverse. By the way, this curve, which is epsilon omega log K, the prefactor epsilon omega was kept the same, whatever we obtained from our DNS. And you get the derivative is epsilon omega K inverse, you balance it by viscous dissipation, you get a K raised to -3 scaling. Now, of course, as you reduce the Reynolds number, what you would have is that these fluxes become less and less dominant. So what you expect is indeed, as Lance and Batal had argued, that at low enough Reynolds number, indeed, all these transfers would become smaller and smaller, and whatever is the energy injected by bubbles would get dissipated in very near vicinity by viscosity, right? And that but kills whatever is the scaling region, -3 scaling that you would get. And indeed, that was observed in earlier numerical simulations at much lower Reynolds number also. So this is nice. What we find, therefore, is that the argument of Lance and Batal, although in details you might question it, but in its spirit, that the net production is indeed epsilon omega times K inverse, it's correct. But the net production has contributions both from surface tension and the nonlinear transfer. So now you can ask then the question, where is this energy flux locally distributed, where you have regions of large upscale transfer or large downscale transfer? So what we did was similar to what INFN had done. We looked at, in homogeneous isotropic turbulence, of course, earlier, we looked at the nonlinear flux in real space. And what we find is that as you go on increasing the filtering scale, so at small scales, you have at the front of the bubble, there is the energy transfer to large scales. And the back of the bubble, there is an energy transfer to small scales. And then you have regions of interspersed red region. Sorry, I said something wrong. At the front, you have energy transfer to small scales, and the back, you have energy transfer. The blue is transfer to large scales. And then, but back region is interspersed with red regions, which is again telling you that there is still a small scale transfer there. So that the net transfer is towards small scale. So wakes predominantly transfer energy to small scales. But as you go on increasing the filtering scale, what you find is a structure that resembles the Stokesian flow. So if you look at far away or at much coarse-grained scales, the flow around the individual bubble indeed looks like what you would see for a Stokesian flow. So indeed, therefore, at very large scales, you would observe that if you looked at the net transfer, it's 0. So that's the picture that one has then about the local transfer. Now the question, let's ask that, so this is more or less explains what happened in the experiments in the regime when the Galilei number was between 400 to 800. But well, you know, experiments could hit that range. Let's ask the question, what happens if we go beyond? What happens if we start to find, as I'd shown you for a single bubble, that the wake of the bubble itself starts to become turbulent. And that's clear from these 2D cuts, that if you see the wake of an individual bubble, it looks like, that the flow has become homogeneous and isotropic. So that was fantastic. And we thought, all right. So most probably what we should observe is that as we go on increasing the Galilei number, if you look at the 1-point PDF of velocity, remember I had told you that in the horizontal components of the velocity, you had exponential tails, would you still observe exponential tails? Or because it looks turbulent, so everything should become Gaussian? Let's see what happens. Surprisingly, you find that there is no difference in the liquid, unless you look deep in the tails, there's no difference in liquid velocity fluctuations. The core of the PDFs just lie on top of each other. So that's truly remarkable, that although we see something which looks like turbulence, it looks like homogeneous isotropic turbulence. But when we look at details, we don't see any signature of it. There is nothing like things are not becoming isotropized, say, or they are, sorry, not isotropized, but things are not becoming Gaussian. All right, but then let's ask, how does the energy spectrum looks like? And then you have a surprise. The energy spectrum shows remarkably a 5/3 region appearing. So what you observe is the following. So what I have plotted here is all the data that we have on a single plot with increasing Galilean numbers. Now, wherever you see this data coming down, that roughly corresponds to the bubble diameter scale for that run, okay? What we claim is that at these high Galilean numbers, there is a new scale which emerges. That new scale is somehow like a Kolmogorov scale in standard homogeneous isotropic turbulence, determined by whatever is your viscosity and the energy injection by buoyancy. So what you then claim is that, there should be a new scale, which we call psi, which is nu cube by energy injected by buoyancy raised to the power 1/4. So the claim is from bubble diameter to the scale psi, you have a 5/3 scaling. And then from the scale psi to smaller scales. How small? Within our numerical simulations, as small as you get. So it goes even penetrates inside the dissipation range. You have the pseudo-turbulence present, where you have a scaling which is completely determined by the balance of net production with viscous dissipation. And all this data falls onto a universal curve. So that's really remarkable. And I think this is a really nice finding that within just flows generated by a bunch of bubbles which are rising, gives you a non-trivial flows. And something which I find is remarkable is that for scales which are very small, sub-Kolmogorov scale, you don't have something like a smooth flow which is exponentially falling, but rather you have a regular flow which is determined by the balance of energy injected by the surface tension and the nonlinear transfer if they are still present. But at those scales, it would be primarily surface tension and the energy dissipated because of viscosity. So how do we check whether whatever I said is true or not? Well, again, look at the energy budget. And let's look at the case from left to right. So at leftmost is Galilei at 302. You see that you have you have both nonlinear and the energy transfer due to surface tension present. They're comparable in their magnitude. If you add the two, which is the net flux, that's the purple curve. This flux balances viscous dissipations for scales which are larger. So this vertical scale is k eta. For scales k greater than k eta, that's the balance. And for scales smaller than k eta, you have no appreciable nonlinear flux present. So you would, in this regime, you would primarily see a -3 scaling. As you increase the Galilei number, you start to see an appreciable nonlinear flux start to develop, which is with this large plateauing happening over here for k less than k eta. And that should show up in a small -5/3 scaling range. You further increase the Galilei number. Now the surface tension transfers becomes completely subdominant for k less than k eta. You have a large nonlinear transfer, which is happening. And so in this regime, as I'd shown you earlier, which would correspond over here, you would observe the -5/3 scaling. And for scaling which is smaller than the psi scale, you observe the -3 or a pseudo-turbulent scaling. Of course, motivated by whatever we saw in our comparison between experiment simulations, we believe that if experiments were to be done at these high Galilei numbers or in natural systems where such high Galilei numbers are indeed present, you should observe these kind of velocity flux or such kind of spectrum to be present. So let me go ahead by first concluding this and then finally tell you about the last part of the story. So at least from here, what the story that we have is that if you are at moderate Galilei numbers, which are Galilei less than 1,000, where most of the experiments are, for k greater than kd, and here it so happens the size scale which I talked about is comparable to kd, you have the -3 scaling. And when you go beyond Galilei of 1,000, a new scaling range appears, where from the bubble diameter scales to an intermediate scale, you observe Kolmogorov-like turbulence, although with the single point velocity fluctuations exponentially decaying. And for k greater than k psi, you have a k raised to -3 scaling. And quite incredibly, our conclusions do not depend either on the density contrast or viscosity contrast. And of course, we are now thinking of how to characterize these things better. But now let me end by finally telling you about another set of experiments where you had bubbles. And again, as I'm saying, they are experiments. So the Galilei number is less than 400 and you have large scale stirring present. Now you ask the question that in such a scenario, what happens? And the claim there is that, well, in this regime, you would observe a -5/3 scaling up to the bubble diameter scale. And beyond that, within, these scaling laws, with these scaling ranges, you would observe a -3 scaling. And so let's see whether we observe this and can we explain this very quickly in a simple way. So first thing is what happens to the bubble trajectory as you go on cranking up Reynolds number. As expected, if you have large scale stirring, they should make the trajectory more curved. And indeed, that's what we observe, that if you make the PDF of curvature of a single trajectory, it becomes more and more curved as you reduce this B parameter or increase the Reynolds number. The average rise velocity of the bubble also, of course, decreases as you increase the large scale stirring in the system. So that's not surprising. The interesting part is, though, what experiments observed was that if you look at the wake flow of the bubble in presence of large scale stirring, actually the wake region diminishes. Okay, so which means that large scale stirring kills the coherent wakes which are produced by the bubbles. Now, if you see it, we checked it in our simulations, and quite remarkably, we find that if in absence of stirring, you have a very deformed ellipsoidal bubble, and this is the average flow. So what we have done is taken many realizations of the bubble and superimpose the velocity field in the center of mass plane of the bubble, one on top of the other. And what you then find is that the flow has nice streamlined structures and you have internal circulations. But the moment you switch on turbulence, the flow becomes, the flow more or less looks same, but the bubble becomes more circular or more spherical rather. And that's nice because that's telling you that the bubble is deforming, tumbling. So on average, its deformation reduces. And if that's the case, then you straight away expect that its wake would be shorter. And also, the ambient turbulence is completely ripping apart whatever is the coherent structure. And indeed, what we find as if you look at the velocity in the center of mass frame across through the center line of the bubble, you see that the velocity drops down fast as you increase the Reynolds number or reduce P. This is the same which was qualitatively observed in the experiments of Riso and others, where they tracked individual bubbles and tried to see the wake flow around the bubble. What happens to the velocity fluctuations? Well, of course, you again, with the arguments that I told you earlier, here, quite contrary to high Galilei number simulations, which also look turbulent, what you find is that indeed, if you have large scale isotropic stirring, the flow becomes more and more isotropic and Gaussian. So you see, as I am going on increasing the bubbulence parameter, the B shown here, the velocity PDFs becomes more and more Gaussian. So that's again what you would expect. If you now look at what is the energy spectrum in presence of stirring, you have something remarkable. You see that now similar to experiments up to certain scales. So the green curve, so not green, but the dark green curve over here, I hope you can see my mouse, is the energy spectrum in absence of bubbles. So you have pure Navier-Stokes simulation. You see a 5/3 scaling followed by decay. And then if you have bubbles in the system, what you observe is that you have a 5/3 scaling again maintained for a short region. Then there is a crossover, which is followed by the -3 scaling. When you increase the Reynolds number, you go from 79 to something like 110. Now you have a longer or a broader 5/3 range, of course. And then again, you have a short region of -3 scaling. And then again, there is, a crossover to the dissipative scales, which we are not completely sure of. I mean, we believe that this part is a numerical error. What we should observe is that this thing keeps on going down. And so what we claim is that for K smaller than the bubble diameter, you should observe a -3 scaling in presence of external stirring. So this is for K larger than the bubble diameter. You should observe EK, which goes as -5/3. And for K greater than bubble diameter, KD, you should observe energy spectrum, which is again -3. Now, I would like to remind you again that this is in contrast with the high Galilei number simulations that we had done, where you expect that, the energy spectrum shows K raised to -5/3 for K greater than KD up to an intermediate scale, which is controlled by the energy injection. And then for scales smaller than that scale, you start to observe a -3 scaling again. So that's more or less the picture. If you now look at the energy budget in presence of stirring, what you observe is that for scales smaller, so if you don't have any bubbles or anything, you only have large scale stirring, then of course you observe that the red curve is that the energy injected by stirring. Remember, these are cumulative curves. The blue curve is the nonlinear flux, and at scales much smaller, at K very large, you have the viscous dissipation coming over. So at these scales, you would observe -5/3 scaling and then crossing over to the standard dissipative scaling. On the other hand, when you have only bubbles, remember you have energy injected by buoyancy now, which is shown with these red triangles. Then you have a small nonlinear flux. You have energy transfer due to surface tension also present. You add the two. You have the net transfer, which is shown with brown color here. And it's this net transfer which balances viscous dissipation to give you -3 scaling for Galilei numbers, which are less than 400. As you further increase, now when you switch on the turbulence stirring, what happens is that you have a dominant nonlinear flux for scales which are which are larger than the bubble diameter, or K smaller than KD. You have a dominant nonlinear flux. However, for scales which are K much larger than KD or scales smaller than the bubble diameter, it's the surface tension which is the dominant energy transfer mechanism. Till these intermediate, for K smaller than KD, because the nonlinear flux is important, you would expect to observe -5/3 scaling. On the other hand, for K greater than KD, therefore, you expect to observe -3 scaling. As you further increase the turbulence intensity, now indeed, for large scales, for K much larger than KD, the nonlinear transfer completely overwhelms any other transfer mechanism. And indeed, in this region, you see a very nice 5/3 regime up to K less than KD. And for K larger than KD, the net transfer again is due to both the surface tension and the nonlinear contribution, which then balances viscous dissipation to give you a pseudo-turbulent scaling, which could be the K -3 or a slope which is larger, depending upon what are the Reynolds number, Galilei number felt by bubbles at these scales. So therefore, we conclude that at large, if you have large turbulence stirring present in the system, then for scales which are larger than the bubble diameter, you have the nonlinear transfer, which is the dominant energy transfer mechanism. However, for scales which are smaller than the bubble diameter, both nonlinear flux and the transfer due to surface tension are present. Which of the two dominates depends upon what is the stirring intensity. And okay, here we had just cross-checked that we indeed have the -3 scaling present in the system, but I think I'm already close to my time. I think I'll leave 10 minutes for question. So with that, let me come to the conclusion slide. So what we have shown is that in presence of large-scale stirring, you have energy injected by a turbulent forcing, which is transferred to the bubble scale by the advective nonlinearity, which gives you -5/3 slope, or the spectrum standard Kolmogorov turbulence. And then at scale smaller than bubble diameters, you have a pseudo-turbulence present. This picture is going to be only true as long as your Galilei numbers are moderate, that is less than 400 or 800. However, if you go larger than much larger Galilei numbers, clearly a new regime will appear where you could see an extended -5/3 up to the scale where you have scale determined by or the scale psi, which is determined by the energy injected by buoyancy and viscosity. And then, of course, beyond that scale, again, we expect the pseudo-turbulence to appear. And quite remarkably, our conclusions do not depend either on the density or viscosity contrast of the system. What happens in 2D? Well, again, here you find that at large enough Galilei number, you do observe a -5/3 scaling via inverse cascade. But for scales k greater than for scales k greater than kd, or for length scale smaller than the bubble diameter, you don't have entropy cascade. Rather, you have pseudo-turbulence present. So with that, I stop. And yeah, so if there are any questions, I can answer them.
Thanks a lot, Prasad, for a beautiful talk. And are there any questions? Yes, please. I don't see the person, but you can go ahead.
This is Ganesh. Prasad, can you hear me? I'm on my mobile.
Yeah, I can hear you. Yes.
Okay, so I was wondering as to what you have in mind when you
Sorry, Ganesh, I can't hear you anymore.
Talk about surface tension involve. What do you have in mind when you're talking about a surface tension driven transfer to small scales?
So what I have in mind is that, so you see, if I have a bubble and if I have to deform it, right, the kinetic energy has to be transferred into an elastic energy, correct? And then when this bubble relaxes, it would undergo some kind of capillary wave oscillation, or it would undergo undulations, which then generate small scale vortices in the vicinity of bubbles, which then injects energy back into the fluid. So that's how I am thinking about it.
Okay, so this doesn't involve a nonlinear capillary wave interaction to generate.
So in the energy transfer mechanisms that I've written down, all those things would be present in the system. What I told you is a very qualitative way, but you know, all the interactions, because you see, when I write down the equations and I write down the scale by scale energy budget, and when I write down the transfer for the surface tension, all those interaction terms, which of course, unfortunately, we are not able to decipher or decouple one from the other, are present in the system.
Okay, so what you're saying is that the surface tension also has nonlinearity hidden in it. So
yes.
Okay, thank you.
Because you see, Ganesh, the way the couplings are, it's a nonlinear coupling between velocity and the surface tension force, right? Which couples different length scales.
Right.
So continuing on the same point, when you have large scale steering and you showed us that these deformations are on average isotropic, you still have this mechanism, or it's just reduced?
It's just reduced. The mechanism is still present. You cannot switch off the mechanism. That's why I said that, you see, the scales at which you would start to feel it, you have to go to smaller and smaller scale where the non-linear transfers would completely disappear. So what we find is that as you go on increasing the, and it's not only us, even others, so once people started to check it, that if you go on increasing the resolution, it goes all the way up to the smallest scales, because the balance is between viscous dissipation and surface tension, right? So when one then thinks of bubbly flows, even when you have small bubbles, which you could allow for small deformation, you would have these mechanisms present. I mean, to say even small particles, right? Which I'm not talking about micron-sized particles, but particles which are slightly larger. And you are even in the Stokesian flow regime, I would argue that, you know, these mechanisms, though very small or subdominant, would be still present.
Okay. Any other questions? So, and this would be a problem for all modelization of point-like bubbles, or if they are very small, this effect is so reduced that then...
No, so as I showed earlier, right, if the particles are very small, or if your Reynolds number are very small, the difference between energy injected by, so if you look at this plot, okay, wait. Okay, I think this is the, yeah. So you see, if you, even at Reynolds, where you went down from 300 to 100, this gap between the energy injected, the scales at which the buoyancy is injecting energy and the scales at which the viscosity is dissipating is gradually reducing. So what you would expect is that if you go all the way down to the Stokesian kind of regime, or if you're small enough bubbles, the other contributions would be very subdominant. You would indeed have, at those small Stokesian flow, I mean, those kind of flows, you need not worry about these mechanisms. They would be completely subdominant.
Prasad, another small question, if no one else is, could you comment on concentration fluctuations? Is there any clustering or non-trivial number density fluctuations that you might observe?
So Ganesh, within at least so we work at small volume fractions. Okay, our volume fractions are around 2%. And for the range of Galilei numbers we looked at, within our setup, which is periodic, and buoyancy, we didn't find much clustering in our 3D simulations. Okay. However, I must point out that if we put in walls, then there are non-trivial effects which can come in, where, you know, bubbles, migrations and other things, which can change some of the things. But because, you know, our idea was to compare with experiments which are typically looking at the bulk properties of the flow, we didn't observe any clustering, and even in the experiments, in these kind of experiments, not much clustering is observed.
How many bubbles did you have in your domain typically?
Yeah, so they vary. So they go from something like 40 to 80 at moderate Galilei number, but at large Galilei numbers where we have large bubbles, we have something like 13 or 14 bubbles. So the bubble numbers are also not very large to, you know, identify clustering very clearly.
Right. Okay.
Right.
Thank you.
But I must tell you that we are doing something else, which hopefully will be out soon, which is again motivated by experiment where you have bubbles in a Haley-Shaw geometry. And there you do observe some kind of clustering appearing in the system. And that, but that's a completely different problem altogether.
Okay, thank you.
So are there any other questions? If not, thank again, Prasad.
So thank you. Yeah.